Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome my mathematical brother, Andre Cornell, who will tell us about quantizing discrete structures. Andre, it's all yours. Take it away.
Thank you very much, Peter, for inviting me and for hosting. And thank you all for coming to the talk. As other speakers have remarked, this is a 90-minute talk, and I decided that this gives me some options. And I'd like to, instead of telling you about a single result, tell you about a thread in my research, and also use the time for a little bit of editorializing. But before I get to the editorializing, I want to give you an overview of the talk. So the talk describes essentially a quantization scheme for classes of discrete structures. So in brief, this means that for each class of discrete structures, we obtain an injective function from the discrete structures into some class of equipped operator algebras. And of course, the whole premise in noncommutative geometry is that the range of this thing should consist of exactly the commutative algebras. The scheme is prescriptive when classes are understood intentionally, in other words, as definitions. On the other hand, equivalent definitions may yield distinct quantizations. So the game here is you pick the right definition of the class you're interested in, and then you get some essentially quantized class. And in practice, the choice of a suitable definition is fairly straightforward. So you don't need to tinker a lot with picking exactly the right definition before you get something quite reasonable in the output. Okay, so a talk outline by items. First, I'll talk about the basic principles underlying the quantization scheme. And one of the things I want to emphasize here is that, in a sense, we're getting quite a lot for almost nothing. Then I'll talk about the quantization of binary relations. And I'll summarize the quantization scheme in terms of a graphical language for expressing essentially the quantum relations that we're going to be using. After that, the rest of the talk is going to be a series of examples. So we'll talk about quantum graphs as sort of the most basic example, quantum maps, quantum groups, and then a couple of examples from quantum information theory, so quantum graph homomorphisms and quantum graph isomorphism, where the parentheses are meant to help you parse these two phrases. And then I'll talk about the example of quantum metrics, which is a little bit outstanding in the sense that the picture there has not fully crystallized the way it has in the case of these other examples. So that's the summary, and now on to the editorial remarks. We can sort of think about how to classify mathematicians. And the standard way of thinking about mathematicians, of thinking about kinds of mathematical research, is to focus on the structures that they study. But I also think that mathematicians differ significantly in the questions that they ask. So in a sense, the key concept here is the primary object of study, which is the source of motivating questions for the research that you're doing. And I might highlight three approaches to a mathematical subject. First, the pure approach, where the structures are the primary objects of study. So then we worry about things like finding new interesting structures, classifying structures, discovering new relationships between the structures in the subject. There's also the applied approach, where really another subject is the primary object of study. So maybe you're thinking about a particular mathematical topic, but the way your research proceeds is it's focused on some subject outside your subject area, and you're using these structures in order to discover something about that other subject area. And then the third approach is the subject itself becomes the primary object of study. So in a sense, one stops trying to increase what is known about the structures that make up the subject, but rather understand how those structures come about and what the conceptual framework underlying the subject looks like. And here I want to emphasize that I don't mean foundational in a praising sense. I don't mean pioneering or influential. I mean in contrast to these two other approaches, pure and applied. And of course, now the foundational approach is deeply out of fashion. But for a time, perhaps many decades ago, it was far more in vogue. And I think a lot of the people, the researchers whom we respect, engaged in foundational research themselves. So I want to highlight some examples of foundational work in non-commutative geometry to point out that it's not completely alien to the subject area. I would highlight Peterson's Borel algebras, Voronovich's pseudospaces, Weaver's quantum relations as three examples. And these three examples certainly, they inform my own research, and they were formative for me as I was developing my my attitude towards non-commutative geometry. And the thing to point out here is that indeed this work shed more light on the nature of the non-commutative metaphor than it did on the structure of C-star algebras or von Neumann algebras and so on. So indeed, it is foundational in the sense of the slide that I had been describing, the previous slide. So in a sense, I'm making a request of all of you in the audience. Probably the foundational perspective is not as natural to you as it is to me. Very likely you take a pure perspective towards non-commutative geometry. But just for the length of this talk, please try to adopt a foundational perspective, because those are the kinds of questions that I'll be answering. And I won't have really any new interesting C-star algebras or von Neumann algebras for you. So if that's what you're looking for, then you won't find what you're looking for. Okay, getting back to the main thread, views on the non-commutative metaphor, I would say, range quite widely. On the one hand, some people regard it as a useful but flawed heuristic for investigating operator algebras. But other people regard it as basically a robust mathematical structure that is yet to be fully understood. And I should say right now that I'm actually quite sympathetic to both points of view, because I've held both points of view over the course of my career. But when we think about the spectrum, the real question that comes up is, does the non-commutative metaphor have mathematical reality? In other words, is there sort of an underlying mathematical structure there, or is it just a funny way of speaking? And I would say that previously the evidence was mixed, but now the evidence points to yes. And one of the things I'd like to communicate in this talk is what the evidence is and why it points to yes. The main, the heart of the story here is that in the case of discrete structures, the non-commutative metaphor can already be formalized as a single mathematical structure. So in this particular area, the answer just clearly is yes already. And almost all known examples fit into this formalized framework. Before I get into the framework, I want to admit that there are a couple of loose ends. First, there are all of these different notions of quantum metric structure. So there, as I mentioned before, the story hasn't quite settled completely. But also there are different notions of counting measure, for example, delta forms. And it's not yet clear exactly how they should fit into the picture. So should they be interpreted as a measure equipping your quantum set, or should they be interpreted as well, a different kind of quantum set structure that hasn't been fully covered yet. So bottom line, this talk covers the formalized framework, but it covers it informally. What do I mean by that? What I mean is that I could fill up quite a number of slides with essentially formal axioms for what this structure looks like. But I decided that that would be kind of boring, and it's more interesting to think about the concepts, and the concepts sort of let you fill in all the details. So it'll be an informal telling, but underlying the informal telling, there is actually a formal mathematical structure. Okay, so now on to the main thread. I've been talking about discrete structures. These are also known as first-order structures. And the basic ingredients there are sets and relations. So our first order of business is to quantize these ingredients. First, what do I mean by a quantum set? A quantum set is a discrete quantum space in exactly the sense that you all know. So Podlesh and Voronovich defined discrete quantum spaces a couple decades ago now, and in a sense, we could just take that definition and run with it. But to highlight how little we need to develop this subject, let's approach the quantization of sets a priori.
Let me just congratulate you on your perfect pronunciation of Podlesh and Voronovich. Chapeau bas.
Thank you. I appreciate it. I may need to pronounce their names again this talk, and I'm not sure that I'll get it right the second time.
Okay.
But I appreciate the encouragement. Okay, so the basic idea is we know that each set is determined by the C-star algebra of bounded complex valued functions on that set. That's basically a triviality. And the intuition is that to quantize sets a priori, what we want to do is we want to find the right class of C-star algebras that generalize this L infinity of X C-star algebra. And it turns out that this is actually very straightforward to do. We have an equivalence that essentially accomplishes this. One, the property that every massa of the C-star algebra M is isomorphic to L infinity of X for some set X. And that's clearly something that we should want from a C-star algebra generalizing quantum sets. Sorry, generalizing sets. And then this very constrictive, constraining structure theorem, structure condition, I should say, that M is isomorphic to an L infinity direct sum of finite type 1 factors, so full matrix algebras.
May I have a question? Sorry.
Yes.
Every massa of M is isomorphic to L infinity for some set X?
That's right.
For any C-star algebra?
No, for a C-star algebra, the two conditions here are equivalent.
Okay.
So having this very strong property is equivalent to M being of this very special form. To prove 2 implies 1 is a very quick exercise, but I do want to sketch the proof of 1 implies 2 because I think it's a little bit enlightening. So for the forward direction, we apply the theory of AW star algebras. First, we observe that M is an AW star algebra by a theorem of Saito and Wright that says you have an AW star algebra whenever the massas are monotone complete. Then we get that M is actually a type 1 AW star algebra, basically because we have lots and lots of minimal projections from this massa condition. Then we get that, in fact, it's a von Neumann algebra by a classic result of Kaplansky. And once we have that, life is very familiar. We know we're looking at an L infinity direct sum of type 1 factors. And finally, we conclude that the factors are all finite because an infinite type 1 factor is definitely going to have a massa that doesn't look like L infinity of x for subset x. So that's a sketch of the proof in the other direction. Bottom line, this
Can you remind me what AW star algebras are?
An AW star algebra is a generalization of W star algebras, so of von Neumann algebras. And the idea is that it is a C star algebra with 2 additional conditions. One condition is that every massa should be monotone complete, or perhaps bounded monotone complete is the more technically correct term. And the second condition is that the lattice of projections should be complete, or perhaps the set of projections should form a complete lattice. But what Saito and Wright proved is that that second condition actually follows from the first condition, so it's redundant, even though it's part of Kaplansky's original definition.
Okay, thank you.
Okay, so the bottom line here is that if we ask for this rather extreme form of discreteness from a C-star algebra M, that's the same as saying that M has this particular form, an L infinity direct sum of finite type 1 factors. Okay, since we are looking at a von Neumann algebra now, I want to tell you about a whole, well, exactly 5 equivalent conditions for this class of von Neumann algebras. First, the von Neumann algebra has this particular form. Second, every massa is isomorphic to L infinity of x for some set x. So we've seen this equivalence. This was the equivalence on the previous slide. But now 3 more conditions. First, every von Neumann subalgebra of M is atomic. 4, every self-adjoint operator in M is diagonalizable in the naive sense. In other words, it has an orthonormal basis of eigenvectors. And 5, the set of unitary operators in M is ultra-weakly compact. So this sort of recalls Tikhonov's theorem a little bit. The thing I'm trying to emphasize here is that this is a really robust class of von Neumann algebras. Basically, no matter how you try to say that the thing is discrete, you end up with the same class of von Neumann algebras. So I'm going to call these von Neumann algebras hereditarily atomic, and this is in reference to item 3 on the list.
May I have a question?
Von Neumann subalgebra is atomic, so I call the thing hereditarily atomic. Is there a question?
Yeah, so I would like to ask about the last condition. The set of unitary operators is ultra-weakly compact, so I presume that it is not the case in general, but I'm a little bit puzzled since every time the set, or correct me if I'm wrong, the set of unitaries is always weakly star compact, yes? Or
I don't believe that's the case. I may have written something incorrectly in haste, but I believe that this is the correct condition. I think it's the standard story here where you have a von Neumann algebra and the unit ball is going to be compact.
yes.
But a whole bunch of subsets of the unit ball that feel like they should be closed are not actually closed. So that's my on-the-fly recollection of how this story goes.
But is ultra-weakly the same as weak star for
It is, yes.
bounded sets?
Is it the same on bounded sets? I think it's just the same by definition. It's the same on all sets.
By definition. Okay.
Or perhaps not by definition, but you can get a little bit philosophical where the ultra-weak topology is defined by these functionals, where you're allowed to take a countable sum of vector functionals, basically. And then the weak star topology is the topology that comes from the pre-dual, and then you do a little bit of work to show that they're the same.
I
But the
see.
way to think about it is maybe the commutative case. If you have a little L infinity of X, then it is going to be a compact set, essentially by Tikhonov's theorem. And if you have like L infinity of R, of the real line, where it's not a set, it's a measure space, you can play around with, unitaries and projections and so on to basically show that you don't have compactness in a lot of familiar scenarios.
Okay, thank you.
Okay,
So I have a question. Sorry, I have a question.
Yes.
Are there known examples of atomic von Neumann algebras which are not of the type from the first point?
Yes. For example, take an infinite type 1 factor. So B of H, our favorite von Neumann algebra. It is going to be atomic because, well, the minimal projections witness that it is atomic. But we can find a masse in there that is of the form like L infinity of R. And that's
Sorry, could you remind me what atomic means?
The definition of atomic is you look at the structure of the projection lattice, and if the projection lattice is atomic, then you call the von Neumann algebra atomic.
And what does it mean that the lattice is atomic?
It means that underneath every positive element of the lattice is a minimal element of the lattice.
Okay.
So basically, a von Neumann algebra being atomic amounts to having enough minimal projections.
Okay.
The idea is, an infinite type 1 factor is clearly atomic in this sense because it has lots and lots of minimal projections, but it has masses that are not atomic, that doesn't have any minimal projections. All right, so this class I'm going to call hereditarily atomic, pointing to condition 3. And a trivial observation, the commutative algebras in this class are exactly of the form L infinity of X for some set X. So it's reasonable to say that these are the C-star algebras that are going to quantize sets for us. And this brings us to our list of basic principles. First, quantum sets correspond to these hereditarily atomic von Neumann algebras. Notionally, every hereditarily atomic von Neumann algebra M is isomorphic to little L infinity of X for some quantum set X, and that exhausts all of the quantum sets. Second basic principle, the Cartesian product corresponds to the spatial tensor product. That's something that's completely unsurprising for us as non-commutative geometers. One comment I'll maybe make here is it doesn't really matter how you try to define the tensor product, you're always going to end up with the same one. So in general, we're familiar with this phenomenon that there are lots and lots of tensor products. But these algebras are so simply structured that no matter how you try to define the thing, you end up with the same operation. And finally, the third principle, when we go to quantize a set X, it is quantized sometimes to a quantum set X and sometimes to its opposite. So you kind of have to figure out when are you writing X and when are you writing the opposite of X. And just to gloss what I mean by the opposite of a quantum set, I just mean that its operator algebra is formally opposite. In other words, I'm formally reversing the order of multiplication. If I'm talking about an actual set, then obviously the opposite of this set is going to be, well, that same set, because multiplication will be commutative and the opposite operation isn't going to do anything. But in the quantum case, it's quite significant that sometimes you're writing X and sometimes you're writing X off. before I move on, I want to emphasize that these are basic principles and not axioms in the modern sense. You can write down axioms in the modern sense, but for a talk like this, it's better to take a few concepts and see where those concepts lead. And here, maybe it's a good time for me to pause in case anybody has questions.
So I have a question. So I cannot see this as a principle. It's simply the notation for hereditary polynomial algebras. Because
well, it is a principle that's going to guide our quantization scheme. So
yeah,
these are ideas that we will use to determine how to quantize a particular class of discrete structures. But indeed, I'm not making mathematical claims here. Just as, when Voronovich was introducing pseudospaces,
precisely.
In many ways, he was introducing a language, but he was introducing a language that told us what questions to ask, how to prove some theorems. Same idea. Okay, I'll move on. These principles explicitly quantize sets, but they also suffice to quantize relations. And that's the story that I want to go through now. So a definition, very natural one due to Weaver, is that a quantum relation is just a projection in an appropriate tensor product. So this is a straightforward quantization of the idea that a relation is a subset of a Cartesian product. And of course, these things form a complete ortholattice, in fact, a complete modular ortholattice, where we say that two of these quantum relations, in other words, two of these projections, are orthogonal to one another, just in case their product is zero. So nothing new here. I want to briefly mention this notation that I think is more or less standard. I believe it's called leg notation. That is very convenient in this setting. When I have a projection that lives in one of the tensor factors, I'm going to write the appropriate subscript on that projection to place it into that tensor factor. And similarly, I'll use maybe a couple of subscripts to place a projection that lives in a couple of tensor factors appropriately into the large tensor product. So I think this is something all of us have seen before. One thing I want to point out about this notation is it's basically just the way mathematical logic treats variables. These subscripts are basically just formal variables. And that brings me to
just a simple
essentially
question.
now every feature of first order logic has been quantized.
Sorry,
And
may I have a
this
quick
fact is
question?
actually, yes,
Could you go to the previous slide?
yes.
This R should be a simple tensor or not necessarily?
You're talking about the proposition or the definition below it?
No, about the last line, your last line. This R should be a simple tensor or general element in a tensor product.
So the idea is that R lives in a tensor of two of the factors,
Yes.
and RKL lives in a much larger tensor product,
Mhm.
and the KL tell us how it lives in that tensor product.
I understand, but if R is a combination of two simple tensors, so
Well, nothing
No,
changes.
no.
Nothing
It's okay.
changes.
It's okay.
Just put ones outside of KNL.
uh,
So it's basically R
okay,
tensored with a
it's
bunch of
fine.
identities, and then you permute the factors to get the R in exactly the place that it needs to be.
Okay, yes, right. Mhm.
So there's probably a typo one line up, because on the right hand side there should be P probably.
Yes. So I apologize. I tried to find all the typos, but a few always sneak through. Indeed, this K should not be here.
Yeah.
So here I'm just putting the projection P.
Yeah.
And the point of the definition is to show that P sub K is basically just P, but put in the right place.
Yeah. Okay.
Okay. Thank you for pointing that out.
1-0 for us.
Okay. The basic idea that's powering the quantization scheme is that every feature of first order logic can now be quantized. The connectives were quantized by Birkhoff and von Neumann a very long time ago now. The quantifiers were quantized by Weaver, and now we also have a quantization of equality. And it turns out that once you have all of these ingredients, the much maligned quantum logic has a lot to do with noncommutative geometry. In fact, it underlies the entire quantization scheme and all of the examples that I listed on basically a table of contents slide earlier in the talk. Bottom line, we can quantize first order logic. Hence, we can quantize any class of first order structures. And I will call first order structures in this talk discrete structures, basically because it's a terminology that's closer to the language of noncommutative geometers as opposed to the language of logicians. But it's the same thing. So I thought pretty seriously about actually telling you that whole story because I'm very fond of the fact that quantum logic turns out to have so much to do with noncommutative geometry. But I decided to keep the language more familiar. And to do that, what we're going to do is quantize this category REL of sets and relations. In particular, the dagger compact structure of REL is equivalent to first order logic. So defining a class of structures in terms of this dagger compact structure is the same as basically just giving a first order definition. That's what we'll do. So our order of business now is to define the dagger compact category REL and then quantize it. And this is sort of a friendlier version of quantizing first order logic explicitly.
Sorry, could you quickly explain how these quantifiers are quantized in this approach by Weaver?
I'm not sure that I can do a good job of it, but I can communicate the main idea.
Okay.
Basically, the existential and universal quantifiers can be expressed in terms of infima or suprema of projections of the appropriate family, where it would take me, I think, about a minute to decisively connect the right quantifier to the right supremum or infimum. That's the basic idea. The idea is, well, we have a lattice that gives us our connectives, but actually it's a complete lattice. Okay. And the fact that it's a complete lattice is enough to interpret the quantifiers.
Okay, makes sense. Okay, thank you.
I think that's about as good as I can do.
Okay.
So now I'm defining the symmetric monoidal category REL. So I'm basically defining first order logic from another language. An object is a set. A morphism from X to Y is a subset of the Cartesian product X times Y. The composition of two morphisms, in other words, two relations, is just the same as their composition, as though they are maps. So
let me make just a very quick comment. When we recently defined new type of morphisms between graphs, this is precisely what we used. Our spaces X and Y were the spaces of all finite paths in a graph. And then a morphism was exactly a relation in that sense. So we actually use it in practice, and we prove functoriality with respect to this category and so on.
relations are a very natural class of morphisms. I agree with the mathematical community that maps are perhaps more natural, but I would say that relations deserve more recognition.
Yeah.
I'll put it that way.
We needed maps in both directions at the same time. So this is why
Exactly,
we went for
you get a
relations.
dagger structure and everything. Yes. So just instead of reading the definition, let me communicate the basic idea. You think of a relation as a map where you may have 0 outputs for an input or 1 output or many outputs. And once you think of a relation that way, it becomes completely clear how to compose these things. And that's how we're composing them. So that's our composition. Then the identity morphism is the diagonal relation. In other words, the identity map. The monoidal product of objects is just the Cartesian product, which means that the monoidal unit has to be a canonical singleton of some kind. So we pick a canonical singleton, that becomes our monoidal unit. And then for the monoidal product of morphisms, in other words, relations, we're basically just taking the Cartesian product again, but we have to reshuffle the entries of our pair of pairs a little bit. So what turns out to be correct is, well, this expression in terms of leg notation. Basically just the Cartesian product of R and S. And one of the reasons why I'm emphasizing this expression is because when we go to quantize this whole story, we're going to use exactly the same expression in the quantum setting. So that's half the structure. The other half the structure is on this slide. We can take the converse of a relation. This is reversing the direction, as Piotr said. And for the converse relation, we're just changing the order of entries in every pair, and we get a relation going in the other direction. For dual objects, the story is quite straightforward. The dual of every set X is that set. The unit of the duality is this relation singleton times the diagonal. And for the co-unit, we do the opposite thing. It's diagonal times singleton. So a very familiar structure. The unit and the co-unit are basically equality relations. And finally, as we've already observed, REL is enriched over ortholattices. And to tell you the enrichment, all I really need to tell you is when 2 of these things are orthogonal to each other, and they're going to be orthogonal when they're disjoint as sets. So R orthogonal to S, just in case R intersect S is the empty set. And in fact, this structure can be defined in terms of the dagger compact structure. So I didn't need to tell you the enrichment. The enrichment comes from the structure I had previously described. In fact, even the dual objects come from the structure that is described before them. So we're going to use all of this structure to define our classes of discrete structures, but we actually don't need all of it a priori. A lot of it comes from a smaller subset of it. Okay, so we're in the business of quantizing this. And in a sense, the most important question when we go to quantize that story is which quantum relation is the diagonal? And one motivating proposition here is that when we're looking at M2C, it turns out that the 0 projection is the only projection R in M2C, tensor M2C, with the property that R is orthogonal to P tensor Q whenever P and Q are orthogonal to each other. And this is a little bit of a problem because exactly this condition defines the diagonal projection in the commutative case. So it feels like when we pass from the commutative case to the non-commutative case, we basically lose our diagonal relation. But there's a fix, and the fix is to appeal to that third basic principle and op one of the factors. The definition that this gives us is we define delta M to be the largest projection in M op tensor M, such that delta M is orthogonal to P op tensor Q whenever P is orthogonal to Q. So it's basically the same definition we want to use in the commutative setting, transported fairly naively to the non-commutative setting, but in order to get something non-degenerate, we need to op one of the tensor factors. And this notation P op just indicates that we're talking about the projection P in the algebra M op. So in what sense is this thing non-degenerate? Well, we can prove that 0 is the only projection P in M such that P op tensor 1 is orthogonal to delta M. So what this is really saying is that in some sense, delta M has a very large support, as large a support as it could possibly have. So this leads us to the intuition that delta M is indeed the diagonal quantum relation in M op tensor M. And since we definitely want to have identity morphisms in our category, it means that a quantum relation from M to N should not be a projection in M tensor N, but in M op tensor N, because we need our identity quantum relation to be among our quantum relations. So that's our definition. A quantum relation from M to N is a projection in M op tensor N. If we have morphisms, we should know how to compose them. So let R in M op tensor N and S in N op tensor O
Excuse me,
quantum relations.
may I ask you to make precise your... Could you come back to the previous page?
Yes.
So, could you say explicitly what is delta M for M being 2 by 2 matrices over C?
Yes. So the idea is that there we're looking at M2C op tensor M2C, right?
Yes.
And there is a canonical representation of this algebra on M2C viewed as a Hilbert space,
Yes.
where we have one tensor factor act on the left and the other tensor factor act on the right.
Yeah.
And in fact, what we're really looking at there is B of M2C, right? So this delta M is the projection that corresponds to the subspace of M2C that is spanned by the identity matrix.
Okay.
Does that answer your question?
Okay, so the scalar product is the Hilbert-Schmidt scalar product.
That's right, yes.
Okay, thank you.
Okay, so we need to talk about how to compose two of these quantum relations. We have an R, we have an S, and the definition is that S after R is the smallest projection in the appropriate tensor product such that this condition holds. 1 minus that projection, sub 1, 4, this is leg notation, meet delta N sub 3, 2 is orthogonal to R tensor S. So one thing to point out is that this projection and this projection commute with each other. So I could have just omitted this symbol and have us read this as a product of two projections. But what I'm trying to emphasize here is that this is exactly the same definition that gets us the composition of two relations in the classical case. And in fact, it's basically the simplest definition we can write down using the structure that we have of the composition of two relations. So we write it down, it gets us exactly what we need in the classical case, it becomes our definition in the quantum case. And to emphasize the point, when M, N, and O come from sets, then we have this equation that the support of S after R is the support of S after the support of R. So the support is how we go from a quantum relation to an actual relation, an actual subset of a Cartesian product. And this equation is describing functoriality for us. So it's basically saying we have the right definition. And here, before I move on, I should emphasize the connection of this definition to a definition that you have likely seen before. So for M represented on H and N represented on K, we have a one-to-one correspondence between projections R in M-op tensor N and ultra-weakly closed subspaces V of B from H to K that satisfy this familiar bimodule condition for the commutons. In other words, our quantum relations coincide with Weaver's quantum relations. And furthermore, this is functorial, so composing S with R in the sense of the definition at the top of this slide is the same as composing these bimodules. So here we take products, we take their span, and we take their closure, of course, in an ultra-weak sense. And here, one of the things I'm noticing is that I somehow accidentally reverted an edit that I made. I think that reasonably this theorem is due entirely to Weaver. Because, well, he defined quantum relations in sense 2, and he proved the equivalence between 1 and 2 in the case of finite dimensional C-star algebras. So here we're talking about a larger class of C-star algebras, but the proof is essentially the same. So that's a mistake that I regret. All right, so now arguably the two most important slides of the talk, how we actually quantize REL. So now I'm basically giving you the quantum version of first order logic that we saw in the context of REL. An object is a hereditarily atomic von Neumann algebra, one of these C-star algebras that we talked about at the beginning. A morphism from M to N is a quantum relation from M to N, so a projection in M-op tensor N. The composition of morphisms, well, it's given by this complicated looking expression, but basically it's just another way to write a definition, the definition that we saw on a previous slide. The identity morphism on M is this delta M projection. For the monoidal product of objects, we're just taking the spatial tensor product of our von Neumann algebras. Of course, then the monoidal unit is just C. And for the monoidal product of morphisms, we basically just naively copy down the expression that we saw for REL, and we make every subset there a projection. And that's our quantization of monoidal product of morphisms. So that's slide 1. As before, there's a slide 2 for all of the other structure. For the dagger structure, we have to start with a quantum relation from M to N, go to a quantum relation from N to M, and we do this in the most naive possible way. We apply the flip map. We notice that the op is in the wrong place now, so we op everything. And we end up with a projection in the right algebra. That's our dagger structure. Now for dual objects, as you probably expected, the dual of M is M-op. The unit of the duality is this projection one tensor delta M. The co-unit of the duality is this projection delta M tensor 1. So again here, what we see is just a naive symbol for symbol replacement of what we saw in the classical case, modulo the fact that we had to op a tensor factor. So theorem, QREL is a dagger compact category. This structure automatically gives us an enrichment. So indeed, QREL is enriched over complete ortholattices, and you know exactly what this enrichment looks like. You know how to order projections, you know when two projections are orthogonal, and so on. So maybe this is a good place for me to pause in case people have questions. Okay, I'll keep going. When we're talking about the non-commutative metaphor, we always want to place our classical mathematics into our larger setting of quantum mathematics. And this is accomplished with this dagger compact faithful functor from REL to QREL. Dagger compact just means we're preserving all of the structure that I've talked about. Faithful means it's injective on morphisms. In fact, I notice now that I omitted an important word. It should be full and faithful. Full and faithful. What does that mean? It means that when I start with two sets and I view them as these von Neumann algebras, then the morphisms that I had between the sets, the relations correspond bijectively with the relations that I have in QREL. So I don't pick up any new morphisms and I don't identify any old morphisms. This functor is defined in a very straightforward way. We map each set X to L infinity of X. We map each relation R to, well, basically just the indicator function of R. So the standard way of going from subsets to projections, where of course I'm identifying L infinity of the Cartesian product of sets with the tensor product of the algebras. And this is of course something very familiar, so I'm going to do this without comment for the rest of the talk. It preserves all ortholattice structure as well. And not surprisingly, its essential range, so its range up to isomorphism, consists of the commutative algebras. So the intuition is that basically this functor is the inclusion functor from REL into QREL. It tells us how REL lives in QREL. So our quantization scheme looks like this.
I have a question.
Yes.
So, speaking about this inclusion, do you mean this embedding of in the categorical sense?
Yes.
Is the full embedding?
Technically, we have a full and faithful functor, but really we want to think of REL as a subcategory of QREL, even though it technically isn't a subcategory of QREL because, well, the objects of REL are sets and the objects of QREL are these hereditarily atomic von Neumann algebras.
Mm-hmm.
Does that answer your question?
Yeah, thank you.
So this is why the word inclusion is in quotes here, because it's not literally an inclusion of a subcategory, but we want to think of it that way. So here is our quantization scheme. We start with a class of discrete structures. We choose a definition of that class in REL. We reinterpret that definition in QREL, and we thereby obtain a class of equipped operator algebras. The definition is formulated in every case in terms of the structure of REL that I mentioned. In other words, the dagger compact structure and the complete ortholattice structure. Now, as I mentioned, the complete ortholattice structure actually comes from the dagger compact structure, but for the language, it's better to actually refer to the complete ortholattice structure to make the quantization more clear. And the bottom line is that in every case, we obtain a quantization of the starting class in the sense of the first slide. So in every case, this quantization scheme gives us an injection from discrete structures into a class of equipped operator algebras with the property that the image up to isomorphism is exactly the commutative equipped operator algebras. So this is a scheme that achieves the stated goal on the first slide every time. A little bit of an aside, I want to talk about the graphical calculus for these quantum relations. And for us, it's not really going to be a calculus because we're not going to use it to compute anything. It's really going to be a graphical language that we're going to use to concisely express the definitions that we're quantizing. So if we have a morphism from M to N, we depict it like so. It's a box with the name of the morphism inside the box. It has a wire going in labeled by the domain. It has a wire coming out labeled by the codomain. We compose by stringing boxes together like so, which suggests that our identity morphisms, our delta m's, should be depicted just as a straight wire. For the monoidal product of morphisms, we put the two diagrams side by side. And well, we can write down an expression for the braiding in rel, and then naively quantize that expression, and we get the braiding in qrel, which is naturally depicted like this. Okay, so that's graphical elements for the symmetric monoidal structure. Now for dual objects. For dual objects, the usual convention is that when we're talking about the identity on the dual of M, so in this case M up, we draw a straight wire, but it's oriented in the opposite direction. And the advantage of this is that then the unit can be depicted as an arc, like so, and the co-unit can be depicted as an arc like so. And the arcs come with specific orientations, and we just work with the opposite von Neumann algebra to get them oriented in the opposite directions. So that takes care of dual objects. Another very important feature for these definitions is maximum morphisms. So between any two sets, there is a largest relation. And similarly, between any two quantum sets, there is a largest quantum relation. This is the notation, the graphical notation, for the largest quantum relation from C, the complex numbers, to M, the largest quantum relation from C to M up, the largest quantum relation from M to C, and the largest quantum relation from M up to C. And one of the convenient features of this notation is when we're talking about the largest quantum relation, the largest morphism from M to N, it is naturally depicted as two loose ends like this. So the moment you have this in your diagram, you can completely separate the N wire from the M wire and handle them as though they have nothing at all to do with each other. An important feature in this specific setting is that often we have self-dual objects. So what does self-dual mean? It means M op is equal to M. The opposite of M is equal to M. In other words, M is commutative. A self-dual object is a commutative hereditarily atomic von Neumann algebra. And in this case, we don't need to worry about putting an arrow on the wire. So the identity on M looks like this. The unit and the co-unit are just a cup and a cap. The largest morphism from our monoidal unit to M looks like this loose end, and the largest morphism from M to our monoidal unit looks like this loose end. So that takes us through basically all of the graphical elements that are going to show up on in the rest of the talk. Maybe here is a good time for me to pause for questions if people have any. Okay, so then on to quantization. Is there a question?
Yeah, can you hear me?
Okay.
Apologize, I can't catch the words.
Oh,
Yeah, I also cannot make it out. I mean, I can hear the sound, but cannot understand it.
Maybe on chat.
Oh, there is something on chat. Okay. Oh, it's okay. Sorry.
All right. Well, then I'll continue. So here is an example that's really meant to illustrate how all of this works. Let's say we have a relation R on X. We could write down 3 graphical conditions for the relation. Here they are. Clearly, the left condition expresses that R is symmetric because it's basically just an overwrought way to say that R dagger is R. In other words, R converse is R. And this is exactly the symmetry of R. The middle condition expresses that R is irreflexive. And here you kind of have to stare at it a little bit initially to see this. The idea is we produce 2 equal elements. We apply R to the element on the left. So we get some Y that is R related to the X that we started with. And then we compare this Y that we got with the X that we started with. So saying that this is the empty relation is saying that the Y is never equal to the X. So indeed, the middle condition is irreflexivity. And similarly, the right condition expresses that R is entire. In other words, for every input X, there is some output Y that X's are related to. So here we see this loose end notation for maximum relations used to express, in this case, that R is entire. All right, so these items 1, 2, and 3 are essentially tiny lemmas, but they tell us exactly how to quantize, in this case, simple graphs. So here are exactly the same 3 conditions, but we've replaced the sets with algebras. We've replaced the relations with quantum relations, in other words, with projections. And we get that a simple quantum graph is a hereditarily atomic von Neumann algebra M, a projection R in M-op tensor M, such that the left and middle conditions hold. And I could have reasonably made this a little proposition because simple quantum graphs already exist in the literature, and this is how one essentially defines them. But the definition that we have on the slides is so close to the definition that appears in the literature that there's no sense claiming that there's any kind of proof happening here. And similarly, if we throw in the right condition, we're expressing that the simple quantum graph has no isolated vertices. So this gives us a general pattern or an illustration of the general pattern for quantization.
May I have a question?
Yes.
May I have a question? Yeah. Your projection R classically is simply a what? A subset.
It's a subset of X times X.
Of pairs.
Yes.
So in your graph, speaking about graph, you are speaking about what?
Well, in this case, I'm talking about a simple graph. And I would say that a simple graph is a set of vertices that is equipped with a symmetric irreflexive relation.
You are assuming that this is symmetric.
It's
Left and
undirected.
middle condition. Okay.
Undirected graph, right?
Okay. Yes, undirected. No. It's even more special because between every two vertices you have at most one vertex.
Yeah,
one
special
edge.
symbol,
Yeah,
yes.
yeah.
Yes.
Simplicity.
Should I move on or should I say a little
Yeah,
bit
yeah.
more?
Go on.
Okay. So now something that isn't true by definition. Let's look at these three conditions, two inequalities and inequality. So to understand what these conditions are saying, we basically go to the classical setting of REL, and we see what they're saying in REL. And this inequality in REL is saying that F is a so-called functional relation. In other words, REL is a partial function. So for a quantum relation F from M to N, we define a partial quantum map. We define F to be a partial quantum map if this left condition holds. And if furthermore the right condition holds, then we define F to be a quantum map. So it is still formally a projection in the appropriate tensor product. But we're calling it a quantum map if these two inequalities are satisfied. And I'm ascribing this definition to Freyd and Shedroff for the reason that this is actually a very general definition that they made when they were doing research on allegories. So an allegory is a category that is REL-like. And in any allegory, you can define a map by, well, these two inequalities. So in a sense, all we're doing is we're porting their definition to QREL. Now, QREL is not an allegory, but it's close enough to an allegory that a lot of the same definitions make sense. And one more observation here is that the middle condition is equivalent to the right condition. So these are two different ways classically to say that your relation is entire. So just like we have in the classical case for partial quantum maps, these two conditions are also equivalent, also intuitively expressed that F is entire. All right, but what does this have to do with noncommutative geometry? One can prove a theorem. This is a theorem that I proved when I was still in graduate school, actually. Partial quantum maps F from M to N correspond bijectively to normal star homomorphisms from N to M. So this is exactly the kind of definition that we see in noncommutative geometry, and we're recovering it here. And it restricts to a one-to-one correspondence between quantum maps from M to N and uninormal star homomorphisms.
Sorry, what do you mean by normal?
I mean ultra-weakly continuous. Let's say it like that. Formally, the definition is preserving the suprema of ascending nets or bounded ascending nets, but it's equivalent to ultra-weak continuity.
Okay.
And the relationship between the F and the phi here is very easy to summarize. Essentially, when we compose F with a projection P, we have to put a dagger on the P to make the codomain and the domain here match up. We get phi of P. So this sort of equation very much fits with how we think of a unital normal star homomorphism as giving us a map. So it's a pullback condition. And you can see, well, how much further can one take this? So here are almost three of the same condition.
Excuse me, could you come back to this definition
Yes.
of quantum maps and quantum partial maps?
Right here.
Yeah. Left condition holds. Quantum map is the middle condition. So what is the relation between quantum maps and classical maps between sets?
A quantum map is exactly the same thing as a map between sets.
It's the same. And partial quantum map is a partial map?
That's correct.
Okay, thank you.
So it's basically going to be implicit in everything else that I say, that whenever I give you a quantum definition, if you interpret that quantum definition in REL, you're going to get the classical definition every time. All right, so I think we were here. So these are very similar diagrams to the diagrams that we had 2 slides ago, but a few of the things are reversed here and there. For a quantum map F from M to N, we say that F is injective if the left condition holds. We say it's surjective if the middle condition holds. And it actually turns out that for quantum maps, the middle condition and the right condition are equivalent. These are classically 2 different ways of expressing that F is surjective. So unsurprisingly, we get a continuation of the theorem that we saw 1 slide ago, the one-to-one correspondence between quantum maps F from M to N and unital normal star homomorphisms from N to M restricts to a one-to-one correspondence between injective quantum maps and surjective unital normal star homomorphisms. And it also separately restricts to a one-to-one correspondence between surjective quantum maps and injective unital normal star homomorphisms. So again, we recover the usual conceptual correspondence between, well, injectivity in the set theoretic direction and surjectivity in the algebraic direction, and vice versa. So bottom line, everything with maps works out exactly the way we want. Here, I want to make the following remark, that we could look at these 2 diagrams that we've essentially seen twice before for an arbitrary relation R from M to N. So the same 2 diagrams depicting that the relation is total, but now without any assumptions that the relation is functional or anything like that. And here, it's amazing how many typos you find when you're delivering the talk. This F, of course, should be an R. So 2 diagrams about the same relation R. So for commutative M and N, these 2 conditions are equivalent. They're both saying that the relation is total. In general, the conditions are not equivalent. And that is something that is very mysterious and unique to the quantum case. And we will see that this phenomenon actually is not just some, random artifact. It actually plays a pretty key role in how this quantization scheme works. We'll see in a moment that it distinguishes discrete quantum groups of Katz type from the class of all discrete quantum groups. Basically, the inversion map can be, well, not the inversion map, the inversion relation can be total in one sense without being total in the other sense. And that's where the distinction happens. All right, so to point that out, we should first talk about discrete quantum monoids.
Sorry. May I have a question about your last comment?
Yes.
Yeah. So can you explain how the equality between these two conditions is equivalent to the fact that the antipode is involutive? How these things are related?
So I think I could try to talk through exactly why these two conditions are equivalent
Yeah.
for arbitrary, let's say, relation R. So in the classical setting. I don't think that I can clearly explain right now exactly how this connects to the antipode story. Let's put it that way. Maybe. Well, let me say something brief, and hopefully that'll be helpful. In a discrete quantum group, you're going to have an antipode. You can interpret the antipode as a quantum relation. It is always going to be total in one of these senses, namely this sense, the sense on the right. And that's going to capture the intuition that indeed every element of the monoid has an inverse. Because, well, the inversion relation is total. On the other hand, the inversion relation is not going to satisfy this inequality in general. It's only going to satisfy the left inequality for discrete quantum groups of Kac type. I think that's probably as much as I can say right now without making a mess of the explanation.
Okay, thank you.
So discrete quantum monoids, completely unsurprising definition. We have a triple MFE. F should be a quantum map from M tensor M to M. So that's our binary operation. E should be a quantum map from C to M. That's our identity element. We know exactly what conditions we want. They're easy to depict graphically. Here is the equation that says that F is associative. Here is a pair of equations that say that E is the identity for F. And here I'm not labeling the wires because they would all be labeled M. It's the only algebra in the picture. So it would visually clutter the equations without adding anything. So here are our discrete quantum monoids. Now we want to think about ways to say that we have inverses, right? To say that we have a quantum group, a discrete quantum group, we just want to say we have a discrete quantum monoid and there are inverses. So here's one definition. A discrete quantum monoid has inverses if these two mirrored diagrammatic equations hold. So maybe I'll try to talk through the equation on the left to make it clear what it's saying in the classical case. All right, well, the loose end on the right of that equation is the largest quantum relation, classically the largest relation. So really, we're just saying that the relation on the left is the largest relation. Okay, so that's saying that no matter what element of the monoid comes down this wire, there will be some element coming down this loose end. Since this is the largest relation, it sends out all of the elements of the monoid, so that when we multiply the two together and compare them to the identity element, we get a yes answer. So this is a pretty straightforward diagrammatic REL way of expressing that, yeah, we have inverses. And of course, this equation says, well, instead of having left inverses, we have right inverses. So maybe has inverses is terminology that's hiding something. And the thing that it's hiding is we're separately asking for left inverses, separately asking for right inverses. Now we can compare this to asking for an inversion map. An inversion map should be a quantum map I that makes these two conditions true. So I'll talk through one because they're mirrors of each other. So for the one on the left, if we interpret it in REL, what's happening is we have two equal elements of the monoid coming down these two wires. We apply the inversion map to the element on the left. So now we have, well, still an x on the right, and now I of x on the left. We multiply these two together, and this equation is saying that doing all of that is the same as just immediately producing the identity element. So this is expressing that I gives us inverses on the left, and of course the other equation is telling us that I is giving us inverses on the right. All right, so two different ways of asking for inverses. Voss
Excuse me.
Yes.
Could you come back to this definition of the inversion map? So is there a relation between this inversion map and the antipode for a bialgebra?
Yes,
okay, so having inverses is not enough to correspond
well, so far, all
to
I've
the
done
antipode.
is I've defined two different properties of discrete quantum monoids. The way to think of this I is it's basically the quantum relation that's associated to the antipode.
I understand. So if you have, for instance, functions on a finite monoid, then you obtain your quantum monoid, which is by accident classical one. Okay.
Yes,
and then
I think I agree with that. Yes.
Okay, and the property of possessing the antipode is equivalent then to having an inversion map.
The issue is that you always have a relation that's a quantum relation that's associated to the antipode.
Yeah.
But that quantum relation is not always a quantum function.
Even classically, it's not.
Because no, classically it always is. But in the quantum setting,
it's good. Okay. Nothing wrong with that.
The idea is that classically, we know from our undergraduate classes, perhaps taking the undergraduate classes or teaching the undergraduate classes, that these two definitions, has inverses and has an inversion map, these are equivalent definitions. They're just two different ways of defining groups.
Yeah. But I'm interested in the relation between this relation defined by the antipode and this inversion map in the sense of your definition.
I think I may have interrupted the beginning of that last question. Could you repeat it, please?
Repeat it. Okay. So my question was about the relation between the relation induced by the antipode in the case of some discrete quantum group, let's say, even finite quantum group, and your inversion map from this second definition. Is it the same? Or inversion map could be something more general?
They can't be exactly the same because one is a linear map and the other is a projection on a tensor product. There is some way to translate between the antipode linear map and this quantum relation, but I'm not sure that I can tell this story in a coherent way right now. So it's the sort of thing where I would need to sit down and spend a few minutes working out exactly how to translate the one to the other. The idea is, okay, we have this linear map. We can turn it into a quantum relation by carefully working our way through a dictionary. And then if it is a quantum map, it'll be this I. But often it isn't a quantum map, so it won't be this I.
Okay, thank you.
So we have these two different properties that a discrete quantum monoid can have. It could either have inverses in the sense at the top of the slide, or it could have an inversion quantum map in the sense of the bottom of the slide. So the theorem that Voss proved that I want to tell you about is that there is a one-to-one correspondence between discrete quantum monoids with inverses in the sense of the top slide, in the sense of the previous slide, and discrete quantum groups. And a newer result that I want to tell you about is a joint work with Alexandru Cervasitu and myself. There is similarly a one-to-one correspondence between discrete quantum monoids with an inversion map. So that refers to the definition at the bottom of the previous slide and discrete quantum groups of Katz type specifically. So this gives us a little bit of a gloss of intuitively what is the difference between a discrete quantum group and a discrete quantum group of Katz type. Well, in a discrete quantum group, every element does have an inverse, but there is no map, there's no quantum map that picks out that inverse. So I think this is very interesting. It's a little bit mysterious. It has to do with this phenomenon of two different ways that a quantum relation can be total. I hope that in the coming years, it'll become clear exactly what the nature of this difference is. I owe you a definition because I think the terminology discrete quantum group of Katz type is not that common. So all I mean by this is it's the dual of a compact quantum group of Katz type in the familiar sense of, well, there's a tracial state.
Sorry, so what about this theorem of Voss? If discrete quantum monoid, in your sense, corresponds to a quantum group, it means that you have this antipode.
Yes, that's right.
It must have your antipode. So this antipode is related with inverses, but which is a linear map, which cannot be written in terms of this graphical calculus?
It actually can be written. So there is a morphism R that corresponds to this antipode, and it is actually invertible, but it's not a quantum map. So there's something very strange that happens in the quantum setting. In the classical setting, whenever you have an invertible relation, it's going to be a map in both directions, right? But in the quantum setting, you can have an invertible relation.
Is it a relation? Is there a relation in your sense?
There is a relation, yes. There is a quantum relation that corresponds
for me,
to the
it's good enough.
Not a quantum map.
But not a quantum map, of course.
Well, there is a quantum relation that corresponds to the antipode, but it's not a quantum map. It doesn't satisfy the two inequalities that characterize those morphisms that are map-like.
Yeah. So I'm not asking about this antipode being a quantum map, because for classical theory of algebras it is not homomorphism. I'm surprised about its linearity, because it was defined in terms of could you come back to your inverses property?
Here.
Yes, it has inverses. Okay, so this is completely, it's written in terms of this graphical calculus.
Correct.
And accidentally or miraculously, you obtain some linear map. So how this linearity can be derived from this relational or graphical calculus? This is my point.
I can't give you all the details, but I can sketch what happens.
Okay.
So let's take a look at the left equation, the left side. Can you see where I'm pointing?
Yes, we can.
Let's forget about this loose end and just look at the top piece, the F followed by E dagger.
Mm-hmm.
So it's a two input quantum relation. And you can think of this two-input quantum relation as corresponding to the antipode. Now, you have to go through basically some dictionary steps to translate it to a linear map. But roughly the idea is that projections like this correspond to subspaces of a tensor product Hilbert space. A tensor product Hilbert space is roughly a space of Hilbert-Schmidt operators from one Hilbert space to another. And then you can use that subspace to piece together the linear map out of little Hilbert-Schmidt components, little Hilbert-Schmidt pieces.
Okay.
So that's the flavor of the thing. I think to communicate it precisely, I would need like 10 minutes with a blackboard or something like this.
By the way, you have exactly minus 52 seconds.
I got it. Thank you.
Well, so I do have a number of more slides prepared, but maybe the right thing for me to do is to skip to my thesis statements so we can have something to discuss. All right, I think I'm seeing a thumbs up, so that's what I'm going to do.
Yes.
All right, so here I was going to tell you about the graph homomorphism game and also the graph isomorphism game, which shows up quite naturally in the setting of this quantization scheme. I was going to show you this pretty slide for quantizing metrics, and explain that it actually does recover a notion of quantum metric in the literature. But then I was going to finish up with some thesis statements, least controversial to most controversial. I figured this is the kind of entertainment we would all appreciate at the end of a talk. So the things I want to convince you of basically in this order are as follows. In the case of discrete structures, the non-commutative metaphor has been fully formalized. So there is a mathematical structure, this inclusion of rel into qrel, which is the non-commutative metaphor in that special case. Second, the formalization is entirely canonical. You basically don't have to make any choices. It should have been worked out a while ago, actually, right? All you do really is you start with how do I quantize sets, and then everything basically falls out inevitably. You don't get to make any real choices along the way. 3, the non-commutative metaphor as a whole, I think, is also a mathematical structure of the same kind. It hasn't been fully formalized. It hasn't been fully understood. I think this is a really interesting problem that I'd like to keep working on. 4, formalizing and understanding the non-commutative metaphor is important for the long-term future of the subject. It's important for the long-term future of the subject for 2 reasons. First, as the subject develops, we will not only want to be quantizing various structures in an improvisational way, but we will want to be relating these quantizations to each other. And for that, we need a coherent, consistent, overarching framework. That's reason 1. Reason 2, if there is a mathematical structure that is the whole non-commutative metaphor, I think it is very difficult to believe that such a thing would have nothing to do with quantum physics. I think that means that if we plan to keep applying non-commutative geometry to quantum physics in a robust way, we need to understand what the non-commutative metaphor actually is and how it relates to the physical world. And then most controversially, I think that non-commutative geometry is currently accumulating a conceptual debt that will need to be paid eventually, because already the literature is growing with lots of quantum generalizations, and very often they don't quite fit together in a coherent way. And right now we're just accepting this as, well, that's life. That's how noncommutative geometry goes. If it is true that there is a mathematical structure that is the noncommutative metaphor, eventually people will have to go back into the literature and adjust all of the definitions to get the quantum generalizations to fit together the right way. So a debt that eventually will have to be paid, maybe not by us, but by other researchers in the area.
And let me add, but we will have to be paid with interest.
For me to end on, so let me end there.
Thank you so much for a very exciting talk. Yes, I was trying to say I would amend your point number 5, that it will need to be paid eventually with interest. It's not just a free loan.
Unfortunately, that's the way debt tends to go, right?
I don't know. Before we continue with questions, let me make a very brief comment. I just cannot resist a temptation. I can resist everything except for temptations. So, you see, when I was doing my PhD with Bark, I was working on quantum principal bundles as a loose metaphor, and okay, it looked like something, and so on and so forth. But then at a certain moment, it took us a decade, with Paul Baum and Kenny Comer to prove that Peter-Galois theorem and actually prove that this approach is fully consistent with classical topology, and every single compact house of topological principal bundle is in fact a special case of what we consider. And this was very tough to make this loose metaphor coming from Hopf-Galois theory rigorous. And we did to compact principal bundles what Voronowicz did to compact groups. I mean, he just took compact groups and he showed them as giving you a subcategory inside his compact quantum groups. So we did the same just for compact quantum bundles, but this was a very tough cookie. And we're struggling for a decade to prove it, that things are coherent and definitions agree. And whichever way you look at it, algebraic, sister algebraic, or categorical, strong monoidality, Hopf-Galois condition, or Elwood's density condition, it's all equivalent. But this was very hard. And I fully support this point of view. Okay, questions now.
Maybe I can respond to your comment with a comment.
Oh, yes, go ahead, yes.
I'm certainly not arguing that research in noncommutative geometry has to start with research on the noncommutative metaphor.
Yeah.
Everything that I talked about and was planning to talk about was discovered in this sort of improvisational way that is common to our subject.
Yeah.
What I'm really arguing is I think our understanding of the noncommutative metaphor should keep up with the cutting edge. It shouldn't fall too far behind the cutting edge.
Yeah, I agree. Adam, you want to ask a question?
Yes, I have more than one question. So since you've ended on a philosophical note, I would like to ask you, how do you view B of H as a non-commutative what?
Yeah,
The
it's
whole B of
non-commutative.
H, where H is infinite dimensional.
I would say to me it is a non-commutative measure space. And one of the major stumbling blocks for this subject, one of the major obfuscations I think that mathematics has thrown in our direction, in our way, is that it's very natural to think of B of H as generalizing sets, that there's a kind of quantum set there, so that L infinity of that quantum set is B of H. But there is, at this point, a mountain of evidence that that is the wrong way to think of B of H. And in fact, it's a measure theoretic object. It's not a set theoretic object.
And what reason do you have in mind? Yes, but I'm curious, what reason do you have in mind?
That's, I think, a pretty long story. Maybe I'll throw out one. So one feature that we have in P of H. Sorry?
So maybe it's too big to be hereditary atomic.
Yes, so mathematically that's the reason. It's just not hereditarily atomic. The question is, which of the equivalent conditions do you point to say, okay, clearly it's not a quantization, it's not a quantum set? The one that I would point to is that if it were a quantum set of some kind, every massa would have to be atomic. It's just, it's not okay to have little L infinity of a thing you're calling a quantum set and have a massa in there that looks like L infinity of the real line as a measure space.
And how about the non-commutative version of stone-check compactification? Are you sympathetic to this idea?
So this is a very personal question for me. And the reason it's a personal question is that for a number of years, I stepped away from noncommutative geometry. And the reason that I stepped away from noncommutative geometry is precisely this issue that you want a stone spectrum for, let's say, unital C-star algebras, a quantum version of that. And there just isn't a version of that story in noncommutative geometry that's fully satisfying, that fits with the parts of the noncommutative metaphor that I personally feel confident about. So my answer is, I don't know exactly how that part of the story should go yet, but I'm optimistic that we're going to get there.
Okay, thank you. One more question, and in fact, it's question slash comment. Since if you have this hope that somehow this non-commutative metaphor should be something like a quantization and could be done canonically and also have some connection with physics, then you are somehow subscribing to idea that somehow this quantum picture should be probably unique. And one could argue that the classical world is just averaging of many details which are unimportant. So there could be very many quantum situations which leads to the same classical picture. And
Yes.
I'm curious, what is your opinion on this argument?
I'm very sympathetic to the argument. I think for most of my career, I was a little bit skeptical of quantization as a notion because it feels like it's going in the wrong direction. In other words, it feels like there is no reason to expect that, for example, you can take a classical structure and then figure out exactly what quantum version of it exists in physical reality. It's more reasonable to take a quantum version of something that exists in physical reality and then try to see what is it going to look like classically.
Exactly.
So I'm still persuaded by the argument to some extent in some cases. However, in the case of the quantization scheme that I've described to you today, I think there were so few choices. There were essentially no places in the argument where one could reasonably do something other than what one ends up doing. And because of this, I feel that this is canonical. And I'm I suppose, taken with the fact that this quantization scheme is canonical, that I'm expecting to see more general versions of the same phenomenon show up.
Okay, I see. Okay, thank you. And my last question is about possible generalizations of many notions coming from set theory, especially regarding cardinal numbers and results which uh, turn out to be independent from the set theory axiom. So, do you expect to somehow similar phenomenon going on in this quantum non-commutative world?
I would say yes, for the trivial reason that the classical world is a sub-world of the quantum world.
Okay, so purely non-commutative, maybe.
I think that I don't expect purely non-commutative versions of the same phenomena. In a sense, I've been telling you about sets, but I'm not really thinking of sets the way set theorists think of sets. What are sets for me? Well, they're very simple topological spaces, basically. They're discrete topological spaces.
Measured spaces.
That's not the perspective that a set theorist has on a set. Set theory is mostly about things like independence results and so on. So even though on some superficial level, the objects of the one subject are exactly the same as the objects of the other subject, I think that mathematically the overlap isn't really there.
Okay, since I'm asking, since there are some results regarding the so-called Calkin algebra, quotient of B of H by compacts, which in fact are somehow independent from axioms of set theory, like an existence of a outer automorphism, for example. There are some theorems in the spirit.
Yes, something like that could happen. I guess it wouldn't feel to me like it is contradicting the sense that I'm trying to express. There are a few results in functional analysis that, well, not results, propositions in functional analysis that are independent or something like this. And I imagine that some of them will be interpretable in non-commutative geometry. But ultimately, I don't think that there is anything about quantum sets from that perspective that is fundamentally different from ordinary sets.
Okay, thank you. Thank you very much.
Okay, if I may, I have a question, but we'll have to go almost to the beginning, i.e. to the moment before you started talking about structures, when you said that you'll be talking about quantum first-order logic, and there were the connectives quantized by Birkhoff-Neumann. This one, yeah. I wanted to ask because on the very next slide, on this very slide, you jumped into the categorical framework. Well, I wanted to ask what happens on the logic side of things, because from what I tried to gather, what you did here, you defined the general quantum first order structures and combined with the different than usual definitions on the logical side of things, you created structures for which, together with these different logical axioms, you can get the satisfaction relation and, in fact, do a, let's say, quantum model theory.
I missed a key word, quantum blank theory.
Model theory.
Model.
Yes, indeed.
Okay. Because I wasn't quite honest, I wasn't sure where exactly the quantization of logic comes into hand, and now that I know that it is in fact quantum model theory, I'd like to ask whether or not you know about some classical theorems known in classical first order model theory that also work in the quantum setting, for example, Wash theorem for ultra products.
This is a very natural question. The answer, unfortunately, is that I have only gotten as far as just quantizing the semantics, quantizing a structure being a model of a sentence, and I haven't gone beyond that basically.
That's far yet. Okay. Thank you very much.
Anybody else?
Yes, I have a question, but I would like to start with a comment. In your scale of, could you go to the last slide? there was a scale very similar to the first one.
You're talking about least
It was a
controversial
scale of
to-
controversiality.
Oh, yes, yes. Page 47, yes. I'm still puzzled how we can have 47 pages out of 44.
I'm also puzzled by this, but I didn't dare to ask this question.
So
I can
my
answer the
impression is
question.
that the points like 3, 4, 5 are to me less controversial than the points 1 and 2. Why? Because you started with all your formalism on the idea of a projection. Okay. Of course, if you speak about von Neumann algebras and minimal projections, then classically they correspond to elements of a set. So it is okay. But when you start speaking about more complicated structures, like for instance, graphs, then your language reduces complexity of the situation to the very simple case, like simple graph, for instance. Okay? So my impression is that the choice of the projection as a basic building block of your construction forgets many specific complexities of combinatorics. For instance, it would be very difficult to speak about quivers in your approach. You have only this, first of all, you don't have these directed graphs, you have only this undirected graphs and only simple graphs. Okay? So this is somehow very simplified context, because in combinatorics you need more complicated structures. I cannot see how these more complicated structures could fit in your picture.
I think I understand the question. The thing that I want to emphasize,
even speaking about graphs, you can have something of which are called multigraphs, undirected, but with many edges between vertices, which you cannot describe as a relation between vertices.
That's right.
So basing all these very complicated, very ambitious formalism overarching all set theory, you are losing very important parts of combinatorics, because not everything is given as a relation, as a subset of Cartesian product, for instance. For instance, among sets, you have also spans, which are very important because they are used to formalize correspondences, which are more general than relations. Very basic mathematical objects, like types of objects, like category, like directed graph, they are using the notion of a span, not the notion of a relation, which is a subset of it. Okay, so category is a very special kind of a span. Simply, for every span, you have a canonical map to the Cartesian product of the domain and counter domain, but this map is not necessarily injective, which means that in a span you can have many kind of edges which go to vertices, project into these vertices. So I cannot see an easy way to speak about this fundamental notion of a span in your language, because your language entirely is based on a subset of the Cartesian product. So what about groupoids? What about categories? What about general spans, correspondences? I cannot see place, a room for these kind of notions. So I agree that the points 3, 4, and 5 philosophical are very important, but this kind of formalization based on such very restrictive notion of a projection, which corresponds to a subset in classical terms, is not flexible enough to fulfill promises from the points 3, 4, and 5. Okay? So sorry for my complaint, but
Maybe you should include the 6th point on this list, that the monotonicity of controversy on this list is the most controversial part.
Well,
no,
I'll
it
have to
was my
decide
first
for my-
impression.
There is a comment in chat, let me read it out. If I may, you can certainly encode directed graphs by losing the symmetry condition. And I believe multigraphs can be described as instance relations between vertices and edges.
No. Even if they are even if they are directed, the problem is that there is at most one arrow between edges. Simplicity is the problem, not direction of arrows.
So I would emphasize in response that the boundary between what I think has been formalized and what I think has not been formalized is discrete structures versus continuous structures. You are describing discrete structures, therefore, my response is that yes, all of the structures that you are describing should be quantizable in exactly the sense that I've been quantizing, let's say, discrete monoids, discrete groups. In particular, we can take the definition of a graph with multiple parallel edges. And this is a definition that can be made entirely categorically in REL. And then we can reinterpret that definition in QREL, and we will get a notion that in the commutative case will recover graphs with multiple parallel edges. Now, this is not an entirely straightforward thing to do because, yeah, you need to pick a specific definition. Maybe sometimes there are two reasonable definitions that lead to two reasonable quantizations, like in the case of discrete quantum group. Maybe you find that, well, every definition that you try, you get something that doesn't do the things you're expecting it to do. But certainly you will get something. Certainly you will get a quantization in the sense of the first slide of the talk.
So it's a quantization of relations. I agree. Everything which is describable in terms of relations, is it quantized well in your project? Yes, I agree. Yeah. But relations are not all what is mathematics about.
Man doesn't live by relations alone.
Yeah. Okay.
I think I didn't catch the comment. Can you repeat it?
Well, there is the saying, man doesn't live by relations alone, right?
Oh, I think in the discrete case, one does live by relations alone.
Okay.
For the example of a graph with parallel edges, as somebody suggested in chat, the standard way to build this in, let's say, an undergraduate mathematics course is, well, you have a set of vertices, you have a set of edges, and you have an incidence relation between the two sets that tell you which edges are incident on which vertices. So this is not a complicated definition. You can formalize it in RHEL, I think, without breaking a sweat. It's something you can do in 10 minutes or so. You can reinterpret it in QREL. You will automatically get a quantization of graphs that allow parallel edges that include all of the graphs you were worried about before. The only question that remains is, okay, is this a quantization that you want to do something with? Is it going to support the sort of theorems you're expecting it to support? But certainly you can go through all of the steps and you can get the quantization.
Yes, I agree that everything formally could be written on many fundamental level. But I see some problem. For instance, if you consider symmetries, okay, then one could say that if you consider symmetries, it is not discrete geometry, because symmetries on the level of category theories, there are some arrows, and if you have arrows, then the categorical dimension increases from 0 to 1. But in combinatorics, if you cannot count configurations, taking into consideration some multiplicities related to some symmetries, something is lacking. Something is lacking in this format.
My feeling is that first, we should not expect everything that is true classically to be true quantumly. As non-commutative geometers, we know that we should not expect this.
Yeah.
Second,
but the ambition. But sorry, but I have to comment on this because it was a very important statement. Because it is a knife in the heart of non-commutative geometry. Because the ambition of non-commutative geometry is to find an appropriate understanding of everything which is classical on this more general quantized level. So if we give up some part of classical mathematics and say that this doesn't survive under some naive quantization, this means that we have to abandon this classical part of mathematics. But the very subject of non-commutative geometries is to find appropriate generalization, maybe not so naive, eliminating classical mathematics, but embracing classical mathematics from more general point of view. So it is very bad that our expectation that not everything classical is satisfied in this quantum realm. It's a challenge. It's not giving up this classical mathematics. It's a challenge of finding an appropriate generalization, rather than forgetting about this stupid classical mathematics. Okay.
I think that before we start formalizing anything, it is very reasonable to claim that we do have a fairly coherent way of thinking about the non-commutative metaphor. And as to the question of should we expect everything that is true classically to be true quantumly, I think certainly not in a literal sense.
Oh, yes.
For example, classically, every Haar state is tracial.
Yeah.
In the quantum setting, there are Haar states that are not tracial. I do not personally view this as a knife in the heart of non-commutative geometry, that this tracial property does not occur in the quantum setting. Rather, I view this as, okay, there is a quantum setting, and in many ways it's richer than the classical setting. So we should expect intricate, surprising, complex things to occur. And we shouldn't abandon the non-commutative metaphor when we discover something interesting.
But let me weigh in a little bit, because I remember a complaint due to Mark, in fact, when he proved the cancellation property for quantum tori. I remember that he complained that the proof that there is cancellation property for quantum tori is so completely different from proving the same from a classical torus. The result is exactly the same. It's just K-theoretical property, but the proofs are totally have nothing to do with each other. So this is another kind of remark about the richness of going quantum.
Yeah, theorems are not formal. You cannot extend formalism.
Yeah.
There is some content which is very difficult to be formalized.
And what we did in our recent paper, Tomek, what we did, we struggled so much to recover this deep, beautiful picture of K-theory of projective spaces by Tia, Todd, and Adams, right? But we had to use completely different methods.
Yes.
Totally different methods. And at the end of the day, we got basically the same depth as a Tia, Todd, and Adams, you know. It wasn't just stupid abelian groups. We had all possible points of view. But it was totally different formalism because it was all quantum. Okay, well, I guess we should wind it up. Anybody else? Any comments? Anybody wants to weigh in? Mark? No. Okay. So in this case, let us thank our speaker again for a very exciting talk.
Thank you.
Give me a second just to stop recording.